Okay. All right, so here's where we're going today. So we have a chapter 2 problem set to work on, and then we can dive into 3, which is where we'll be looking at different kinds of functions. Last time in chapter 2, we focused on linear functions. Now we're basically looking at a specific type of nonlinear function, specifically what we would call polynomials, which just simply means many terms, but there are restrictions on what polynomials can look like. So we'll get to that in a bit. But first, let's look at the chapter 2 problem set. And let's see. Yes, okay, good. So we're going to be looking at, remember, this is what we were doing last time. We're calculating the slope of a line. We're going to find a linear function. We're going to find out if these are parallel or perpendicular. So yeah, this one won't be too bad. Okay, so let me just quickly save this. Today's the 22nd. Okay, so these are pretty straightforward. You have 2 points. And so the idea here is that you should probably just start with the slope. And once you got the slope, then you can substitute it back into the original equation with one of the other points and find the intercept. Okay, so the slope, let's just say that we decide to call this, hold on, let me make this bigger. We could think of this first point as x1, y1, and x2, y2. Not that it matters. Either one is fine. You'll get the same slope and same results either way, no matter which point is x1 and x2. But let's just say that this is x1, y1, this is x2, y2. So remember, the slope is the change in the y's over the change in the x's. And that in turn simply means y2 minus y1 over x2 minus x1. So the difference in the y's is 10 minus 4. The difference in the x's is 4 minus 2. So we have 6 halves, which is 3. Oh, it doesn't even ask for the, I just realized that it doesn't ask for the equation, it just wants the slope. Well, that's so much the better. But if you did want the actual equation, let me just quickly show you what that would look like. It would be y equals 3x plus b. And I'll pick the first point, 2 comma 4. 4 equals 6 plus b, or negative 2 equals b. So in other words, had the question asked you for the entire equation of this line, it would have been 3x minus 2. Okay, but it only asked for the slope. So we'll focus on that. But going forward, this is what you could have done to find the entire equation of the line. All right, well, if that's the case, let's carry on and do the exact same thing here. Now, of course, you don't have to label these, but I think it's a good idea because it's easy to make mistakes, you know, just by copying things wrong. So by labeling everything, that helps cut down on the risk that you simply copied something incorrectly. All right, so what does that leave us with? Hold on one second. I need room. So yeah, we can think of this as the difference in the y's again, 11 minus 5. And the difference in the x's, well, let's do these two, 4 minus 1. We have 6/3, which is 2. Very nice. And they're all exactly the same, at least in this section. All right. And, you know, you have to be a little careful. It's easy to make mistakes too with negative numbers. Just always remember that when you subtract a negative number, what you are doing is in effect adding. All right, let's keep going. So the difference in the y's would be 2 minus 4. difference in the x's is 5 minus minus 1. This is what I was talking about, 5 minus minus 1. Okay, so that's minus 2 over positive 6. And that ends up being negative 1/3. All right, 2 more. I mean, once you get the hang of this, you know, they're all pretty much the same thing. Now, of course, you know, you have to be careful. The only thing we don't want to see is division by 0. If the x's are the same, then the slope is undefined, but we don't have that case here. But if it did pop up, just be aware that if the x's aren't changing, that means the slope is undefined, because you basically have a vertical line. All right, the difference in the y's, here it is. And here it is again, 6 minus minus 2, 4 minus 8. So we have 8 over minus 4, which is minus 2. Okay. So I'll give you a minute to catch up in case you need it, and then we'll do the last one. Okay. All right, one more, and then we can carry on to something else. Okay, so the difference in the y's, 3 minus 11. The x's, minus 4 minus 6. Sorry, minus a minus. No, it is minus 6. Sorry, it is minus 6. So it's minus 8 over minus 10, which you could reduce to 4/5. Okay, the two negatives cancel each other out, and you end up with 4/5. Now, down here, when it says define a linear function, that's just a fancy way of saying come up with the equation of a straight line. Okay, so now here they're doing it a little bit differently, because this is basically y. And this is, oh, sorry, this is x, this is x, this is x, and this is y. I wrote it backwards. This is x, and this is y. This is x1, and this is y1. So sorry, 2. This is a slightly disguised version of what we just got through doing up here. Okay, so by writing it as f of -5, that tells me that x is -5 and y is -4. Over here, that means that x is 5 while y is 2. So now you can calculate the slope. You have 2 minus a minus 4 over 5 minus minus 5. So you've got, this is actually 2 plus 4. This is 5 plus 5. So the slope is 3/5. So now to find the entire equation, you can write y equals 3/5 x plus b. And now you can pick either point and plug it in here. So let's pick the first one. X1 is -5, y1 is -4. So therefore, you could write -4 equals 3/5 -5 plus b. And now what you have is -4 equals -3 plus b. Okay, because this is what you're actually doing. And so you've got -15/5, which is -3. And now if I add 3 to both sides, -1 is b, so the final result is that y equals 3/5 x minus 1. All right, so that was pretty straightforward. As long as you recognize what was going on here with the x's and y's, that was really the only challenging part. Now here, we have the same setup. This is x1. This is y1, x2, y2. All right, as usual, we'll start with the slope. Here we'll have 1 minus, the difference between these two is 1 minus 4. And then we'll have here 5 minus 1. Minus 3, positive 6. And so once again, to find the slope, the entire equation, just write this as minus 1/2 x plus b. Either point will do the job here. Let's use x1, y1. Doesn't make any difference. 4 equals minus 1/2 times negative 1 plus b. All right, so when we subtract a half from both sides, what you could probably do is rewrite this as 8 halves equals 1/2 plus b. And then when you subtract, you should end up with 7 halves. So the final result would be, okay, so remember the slope was negative 1/2 plus 7 halves. That's our equation. Beautiful. Now this is just like the first part. We just have the 2 points. So let's get that done. But now this time, of course, like I said, in the first section, they were only really asking for the slopes. Now we do need the entire equation. But we know how to do that. We know exactly how that works. So we start with the slope. All right, so the difference in the y is 10 minus 4. The difference in the x's is 4 minus 2. 6 halves, or 3. And with that information, we can go ahead and pick one of the points. Let's pick the first one, not that it matters. And plug that in. Oh, you know what? What did I do? Hold on. This is y1. Sorry. Now we're, yeah, okay, we're good now. All right. So it's 2 comma 4. So therefore the y is a 4. The x is a 2. And we have, there we go. So the final result is that y equals 3x minus 2. All right, now number 9 is exactly the same. All right, let's start with the slope. All right, so the difference between the y's is 11 minus 5. The difference between the x's is 4 minus 1. 6/3, which is 2. And then We'll substitute in the first point. 5 is 2 times 1 plus b. 5 equals 2 plus b. 3 equals b. All right, so when we consolidate all that information, y equals 2x plus 3. Now, this next one is a little bit tricky, but even it may appear to be different than what we've been doing, but it really isn't. These are just still 2 points on the line. The fact that one is the x-intercept and the other is the y-intercept actually doesn't change anything. We can still use, now, except for one thing. There is one way in which this is actually helpful to us. Because if you look at it carefully, you'll see this would be the intercept. Oh, no, not there. 0 comma minus 3. This is our b. All right, that's the one way in which this actually matters. The x-intercept is here. So the line looks approximately like this. So what this means then is you can start out by saying y equals mx minus 3. And then once you know the slope, you're all set. So remember, let's call this x1 and y1. Call this x2 and y2. So we'll have minus 3 minus 0 divided by 0 minus 2 for our slope. Okay, and so we end up with 3 halves minus 3. Oh, sorry, 3 halves x minus b. Okay. Anyway, let's see, what's going on here. All right. So now what about these? Okay, now these are very simple and straightforward because all we need to know is whether the lines are parallel, perpendicular, or neither. So how can we answer a question like that? Well, that means we need to know their slopes. That's all we need. But the way they're written, we have to do a little algebra to find their slopes. So for example, with this one, let's see, I'll subtract 4x from both sides. And then I'll divide out by that negative 7. Okay. So I have positive 4/7 x minus 10 over 7. So again, I just subtracted 4x from both sides, and then I divided both sides by negative 7 because I want y to be all by itself on the left-hand side. And then when I see the coefficient of x, then I have my slope. Let's write it like this. M equals 4 over 7. Now, what about this equation? Let's rearrange it. 4y. Let's subtract 7x from both sides. And now divide everything by 4. Okay, so here's the trick. We know that they're not parallel because they have different slopes. Oh, wait, what happened here? Yeah, something got erased there somehow. Wait a minute. Okay, but so, all right, so clearly the lines are not parallel because they have different slopes. What about perpendicular? Well, the product of these slopes, if you multiply these together, you have 4/7 times negative 7/4. And guess what you get? And so because the slope is -1, that implies that these lines are perpendicular. That's what perpendicular actually means. And it just means wherever they cross, there'll be a right angle between them. Okay, so they will cross at a right angle. They're perpendicular. Okay. But it wasn't obvious right off the bat, was it? No. We have to rearrange the equations to make sure that we know the exact slopes of both lines. Okay, right now, that isn't really true, is it? No. So let's look at this one. So we have, let's subtract the x from both sides, divide by the 3. Okay, m equals -1/3. And this one, all I have to do is actually multiply both sides by -1. Okay, so this one's different because if you can see, the lines are not parallel because the slopes are different. They're not perpendicular because the product of their slopes is not -1. Okay, so they're neither. All right, so many lines are neither perpendicular nor parallel. So this is one of those cases. The answer is neither, and you can see we just proved it. All right, let's do the same thing for 13. We start by rewriting the equations until it's in the proper form, y equals mx plus b. So I'll subtract that 4x, divide by 3. Okay, so the slope is -4/3. And then for this here, I'll do the same thing. Oh, actually, this one is already, all I have to do is divide by that -6. And you notice if I reduce that, the slope is -4/3. Well, here we go. You can see they both have the same slope. Since these lines have the same slope, they are parallel. And in fact, if you look at them carefully, after I'm done writing them, you'll notice the only way in which they're different is their vertical intercept. Up here, we have y equals -4/3 x plus 4. Here we have -4/3 x plus 1. So you would, if you can imagine, they would end up looking something like this. See what I can do here. Yes, because in other words, the intercept would be here and here. Okay, but they have the same slope, so therefore they must be parallel. Okay. 14. Okay, so 14, yes. So we'll rearrange them as always. So the first one, you've got let's subtract 6x from both sides. So here you've got a slope of 2/3. And for this one, two y, we subtract the 3x, divide by 2. Okay, so guess what? In this case, the product of the slopes is, as you can see, 2/3 times minus 3/2, which is -1. And of course, we know that means these lines are perpendicular, since the product of their slopes is -1. Very good. Now, ooh, look at this one. The first one is already done. You don't have to do anything with it. Okay. So it's the second one we have to do something with. It's not quite in the form we need. So let's subtract the 3x from both sides. Ah, look what we have. So the slope here is 2/3. Slope here is -3/2, and you can see already that the product is 2/3 times -3/2, -6/6, -1. So once again, that indicates that these are perpendicular. The product of the slopes is -1. Okay, now this one is a little bit different. We're finding the x and the y intercept. Well, we know how to find the y-intercept. In fact, here you can see we already know that the y-intercept is 2, because this is the same thing as y equals mx plus b. So in this case, m is -1 and b is 2. That's the y-intercept. The x-intercept means set this whole thing equal to 0. Okay, so in other words, to find the x-intercept, set the equation equal to 0 and solve for x. So you'll have 0 equals -x plus 2, which is the same thing as saying x equals 2. And that is your intercept of x-intercept. So in other words, let's see if we can sketch this thing out. The y-intercept is 2, 0. And the x-intercept, oh, sorry, this is 0, 2. It's 0, 2 because the y-intercept means when the y-intercept is 2, y is equal to 0. So in other words, this is where it crosses the vertical axis. So when b equals 2, that implies that the y-intercept is the point 0, 2, because x has to be 0 and y is 2. What about the x-intercept? It's the other way around. This is where the function crosses the horizontal axis, which means this is where y is equal to 0. So the x-intercept means that the first point is x, and the second point, the y, is guaranteed to be 0. So when we connect these, you can see the slope is negative. According to this, it's -1, but this is what we're interested in. So you can write these intercepts as x equals 2 and y equals 2. Or you could write these as the points 2, 0 and 0, 2. It means the same thing because these are the intercepts. Okay. What about 17? Well, once again, we already know the y-intercept is this 4. Specifically, it's the point on the graph 0, 4. How about the x-intercept? All right, so subtract 4 from both sides. We'll divide out the 2. Okay, so those are the intercepts. Okay, and if you choose to do so, remember what you're actually doing here. The x-intercept is here, and the y-intercept is here. Okay. Now, what about this one? Well, the y-intercept is -5. Because it's right there. It's staring us in the face. The equation is already in the proper format to determine that the intercept is 5. So the x-intercept will be this. This is our x-intercept. Okay. So that means that we have, let's say, that's our x-intercept. The y-intercept is negative down here somewhere, -5, 0. And this is our line. And the slope you can see is 3, so that looks like it's right. Okay, but as far as the question is concerned, if you wrote down for your answer 5/3 for x-intercept and -5 for the y-intercept, that is fine. Okay, you don't have to draw the picture or anything like that. Now, this next one, again, it's written in a form where we can see easily that the y-intercept is here. The x-intercept, you just simply set this equal to 0 and solve. And so you end up with +1/5 as your x-intercept. All right, so let's see what this looks like. All right, and you can see the slope is -5, so that looks good. Okay. Now this one, for the first time, we can't just read the y-intercept directly off the equation. It's not in the correct form, is it? No, it has to be in this form. We have a little algebra to do with this one. So let's add 2x to both sides. Divide out the 5. Okay, so the intercept is 4. Let me just clean that up a little. Oh, for God's sake. All right, now we can do the y-intercept. 0 equal, I'm sorry, the x-intercept. All right, subtract the 4. And we'll get our intercept. Okay, so -4 is 2/5 x. Ooh, this one's a little tricky. What happens when you divide -4 by 2/5? All right, here's a helpful hint over here. Just remember that in the most general terms, if you're dividing by a fraction, it's equivalent to multiplying by its inverse. And that holds even if a over b is just a single, that, like, for example, that would hold here too. The key is that you're multiplying by the inverse. So therefore, this -4 over 2/5 is the same thing as -4 times 5 halves, which is -20 halves, which is -10. Okay, that's your x-intercept. So y equals 4 and x equals -10. These are the intercepts. And again, you can think of this one as 0, 4, and this is -10, 0. And if you want to see roughly what this looks like, all you need is those 2 points. So 0, 4 is here. -10, 0 is way out here somewhere. And then this is our line. Okay, and the slope you can see is 2/5. It's positive, but not very steep. Nice. Now, here's what we have to do with these. It says determine whether the lines are parallel, perpendicular, or neither. Now, we already did this before, but the information we were given was a little bit different. Here we're given the 2 points. In other words, in order to do this properly, we need to find the 2 slopes, and then we can compare them. Okay, so in other words, instead of being given 2 equations, we're being given 2 points for each one. So luckily, all we have to do is solve for m. And we've done that before many, many times today. So we're getting pretty good at this, aren't we? Of course we are. So the difference between the y's is -24 minus 6. For the x's, it's 3 minus 0. -10. Now, what about this one? And so once again, m equals delta y over delta x. negative 71 minus 19 over 8 minus 1. This is minus 90 over 9. Oh, what do you know? It's negative 10. So since the lines have the same slope, they are parallel. And that's what you need to know. It didn't look like it at first, but there they are. All right, 22. So we've got M. Actually, let me move this down here. So the difference in the y's is 89 minus a minus 55. The difference in the x's is 10 minus 8. Equals, so this one is equal to, so basically you're taking out 89 plus 55, 144 over 18. Now that reduces to, actually, surprisingly enough, that reduces to 8. Is that possible? Yeah, that's 8. How do you like that? Ooh, I wouldn't have guessed. It's 8. Yes, if you divide 18 into 144, it's 8. All right. How about the second one? Okay, let's try that one. Okay. So the y's are minus 14 minus 44. And the x's are 4 minus 9. All right, so we end up with, now this is actually minus 14 plus 44, so it ends up being positive 30. So we end up with negative 6. And of course, you can see those numbers do not match. The slopes are different. The lines are not parallel. And the product of the slopes is not equal to -1. So the lines are not perpendicular. Okay. So 8 and -6, no, that's neither. Fernando.
So it'll be neither then, right?
That's right. This one is a case where they're neither. Excellent. All right, let's do a few more of these. And you see, each time we do one, it gets a little easier, doesn't it? Okay, so this one, let's see. -1, -3 is the difference in the y's. The difference in the x's is 4 minus 2. -2. And now here the difference is 5 minus 3 over 8 minus 6. All right, so we have the same situation here. It doesn't look like the lines are either parallel or perpendicular. Okay, so let's see why. Lines are not parallel since their slopes are different. The lines are not perpendicular since the product of their slopes is not -1. And that's it. So it's neither. And for the most part, the reality is most lines that you choose will be neither. When you think about how many lines there are, the vast majority of them are not going to be parallel to each other or perpendicular. But you never know. Okay, so let's look at this one. Five minus 7, 5 minus 1. Then we have m equals okay, 1 minus 3, 1 minus 1, 4 over 2. That's see, now we're getting somewhere. This one looks promising because let's see, because if you multiply these out, well, first of all, they're clearly not parallel. The lines are not parallel because their slopes are different. But the product of these slopes is -1. If you multiply -1/2 by 2, you get -1. So they are perpendicular. All right, and it looks like there's just one more, and that's it. We're done with the entire problem set. Okay, good. And we got through this without too much difficulty, I think. You never know. Some chapters might be trickier than others. It's hard to tell in advance. Okay. All right, the difference in the y is 3 minus 5. The difference in the x is 3 minus 0. Minus 2/3. And the one directly below it. Let's see. So again, the difference in the y's, here we have to watch it because there's another minus. -2 minus and minus 5. 3 minus 1. 3 over 2. Okay, now look, see what we've got. The lines are clearly not parallel. Because their slopes are different. But the product of the slopes is -1. If you multiply -2/3 by 3/2, you'll get -1. So therefore, the lines are perpendicular. And that seems to be it for these. Okay, good. I'm glad that this one was very straightforward. That gives you confidence, I hope, for whatever exams are coming our way, because the questions on the exams will be just like these problem sets. Plus, you'll have access to all your notes and all the videos and all the slides and all the rest. So yeah, it looks, now before we do have any tests, which will be for not for a while, we'll have another set of practice problems for all the chapters that are covered by the test. So in other words, we'll get another round of practicing going before we even think about having another test. I mean, a first test. So, but don't panic. It's not going to be at least for at least a few more weeks. So let's say maximum 2 or 3 weeks, somewhere along that way, sometime in mid-October, I guess. Early October is probably about when we'll probably do this. And then you'll have at least a week to do it. Okay, Fernando.
So would the test like later on will be like a pretty much all of everything that we covered, right?
Yes, it'll be like the problem sets, exactly. But you're doing this at home, so that will make it a little easier and less stressful, I hope. Anyway, so in the meantime, now all that we have to do today for the rest of the day is look at chapter 3, which it's a little more challenging than chapter 2, but you know what, we'll get there. We'll work on it because these are functions that are not linear. They're different from linear functions in a few very important ways. Now, we're going to start though with a look at imaginary numbers though. We're actually going to take a closer look at them because they may show up as solutions to these types of functions. And so we'd like to do or learn some very basic algebraic techniques for dealing with imaginary numbers. Well, I mean, it doesn't have to be Google Doc. I'll probably put it in Moodle and you can just download it. But yes, it'll be just like the other classes, which I know you've been in them, so you know what to expect. Yeah, that won't change. I'll post it. I would use Google Docs, but I don't know how. So instead I'll post it and then you can just download it from Moodle. Fernando?
I remember you mentioned that like we had like you suggested us to learn how to like write on like the handouts or on the assignments. And I noticed like when you go over class, you do that, like you write over like the questions and whatnot.
Yeah.
I want to ask
Oh, you know what?
like, you know,
I no,
what do
you know
you
what the thing
use?
is?
Like,
I tell you what, what you'll probably wind up doing is just writing it out on paper like you would if you were in a classroom setting, and then taking a picture of everything and sending it back to me. That's usually what we've been doing. If you were to do this directly on it, like I have this special tablet here that I'm using, which I don't want to tell you to spend money on a tablet if you're never going to use it again, which you certainly could if you wanted to, but
got it.
it's just all you have to do is take out a piece of paper and write it down, and then use your phone camera to take a picture of it, or else use one of the scanning. There's some scanning software you can get for these guys. There's a few, and now I'm starting to forget what they were called, but there's all kinds. There's at least 2 really good scanning software applications on the iPhone, which basically take a picture of it as if you were using a regular scanner. And I've never used them, but people have told me that they work well. And we'll discuss this as we get closer to the date. But what people have mainly been doing in the past, when I had an online class, they would write everything down on paper the normal way, and then they would take their phone and then just take pictures of it and then send them back. The only issue we have to watch out for, though, is that the pictures you take on your phone can take up a lot of memory. And so what sometimes was happening was that people would email it back to me and would never get there or end up in my junk box because of the size of the file. So if you know how to use Google Docs, which I certainly do not, you can send them through Google Docs, and then you'll have to explain to me how to find them. All right. But if you do that, I eventually will see them. And so that might be another option just because of the size of the files. But it won't be a problem. The only time it was a problem is that if people were not careful taking the pictures and there was a lot of glare, so I couldn't really read it properly. Just make sure when you take pictures of documents that you can read it yourself before you email it back to me. That was really the only problem that we had. That and the large file sizes, which was a problem sometimes. So, but we will get it straight. Now, the scanning software, I know I had it written down here somewhere, but we'll figure that out too. There do exist apps that are free for the iPhone where you can scan the picture and then somehow that gets turned into a PDF file and you can email it to me. But I can't for the life of me remember what they were called.
You mean Genius Scanner?
Is that the one? Oh my God. I think that sounds right.
Yeah, that was the one that you mentioned earlier.
Oh, okay. Yeah, because you know what? I've got so many apps on this thing. The problem is I let my little niece play with it, and she's got so many little games in here that I can hardly find any of my own apps. There must be a way you can like put all the apps from somebody else into a different section, but I don't know how to do this. So, all right, Genius Scan, that sounds right. But I've never used it myself, so I can't tell you how it works, but apparently it works well. Like I said, the people who have used it told me that it worked very nicely. And when I saw the quality, I could see that it was very good. So we'll think about that. And since it's free, you know, it's one of those things where maybe we can get everybody to use it if it's working so well. So, all right, well, we won't even have to think about this for at least a couple of weeks. So let's get back to chapter 3. And oh yes, as I started to say, we're going to start by looking at complex, well, imaginary numbers. It turns out that imaginary numbers are an important part of what are called complex numbers. Complex numbers are basically a function of imaginary numbers. And most people do not get any actual practice using complex or imaginary numbers in algebraic expressions. So we're going to just briefly review the properties of these numbers because, again, they may show up in some of our equations. And then we can focus on the rest of these, the quadratic functions, which you've definitely seen before, the polynomial functions, which are higher order functions, rational functions, and inverses and radical functions. Now, these all sound very scary, but most of these you've seen before. But let's just start with our complex numbers. Now, let me just see. I don't remember off the top of my head. I want to see, somewhere along the way, I thought I might have grabbed a video about complex and imaginary numbers. Let me just go look at the list. Oh, that's us, yeah. No, maybe not. Maybe I was thinking of something else. All right, well, we'll see how that goes. But right now, let's just quickly remind ourselves that, and this is something you've seen before, an imaginary number I is just the square root of -1. Okay, so when you see the letter I in math, it means the square root of -1. This is called an imaginary number because it is not part of the real number system. Now, I don't know who chose the name imaginary, or not really. I'd have to look that up. Not so sure it was a good choice because it seems to imply that these don't actually exist. But yet, there will be cases where you might actually have imaginary numbers. We'll see some examples as we go along. But it turns out, and I think we mentioned this once before, if you remember, there are a lot of different radicals that you might encounter. Let me just quickly sneak this in here. So if you take the square root of a number, this is equivalent to x to the 1/2 power. If you take the cube root of a number, this is equivalent to x to the 1/3 power. And then you can have, for example, the fourth root. You can have the fifth root. And then so on and so on. Okay. We don't need any more. So first things first, I'll put dots to indicate this goes on forever. These are often known as the even roots. These are known as the odd roots. Why? Because you can see in the exponent, you have an odd number as opposed to an even number. So why am I breaking them up into two categories here? Because what I want to remind everyone is that we can take the odd root. Sorry, yes, that's right. The odd root of a negative number. But we cannot take the even root of a negative number. Or I guess I shouldn't say we cannot. We cannot and still have a real result, okay? Okay, so in other words, within the real number system, we cannot take the even root of a negative number. There's no problem over here on the right-hand side. For example, the cube root of -1 is just -1. So there's no problem with the odd roots. With the even roots, we can't take the even root and end up with a real result. Instead, if we do try this, we'll end up with an imaginary number. Okay, so, and then yes, in general, the even root of any negative number is imaginary. Okay, so the fourth root, this is clearly an even root. And by applying it to a negative number, whatever that we get, it's going to be an imaginary number. Now, technically, if I combine an imaginary number with a real number, the resulting number is called in math a complex number. Okay, you often hear those words used interchangeably, imaginary and complex, but if you want to be really technical about it, a complex number requires imaginary and real components, but it's based on the idea of an imaginary number like I. Okay, and in fact, this one, yeah, you can see it can be either expressed as 3i plus 7 or 3 radical -1 plus 7. It means the same thing. So now the question is, can we do algebra on these imaginary or complex numbers? And the answer is yes. And of course, that has to be the case because under certain conditions, you will end up with complex or imaginary solutions to equations. And you might think, well, how would this ever happen? Let me just give you a quick example of this. You might recall from high school the quadratic formula. And we'll review this again later on, by the way. The one thing I want to remind you then is that if b squared is less than 4ac, we will have the square root of a negative number, complex solutions. Okay, in other words, the solutions will be complex numbers, meaning that there's an I involved and there's real numbers. And so this is a case when you might actually bump into these types of solutions. Now, when you were in high school and doing this equation, they made sure that this never happened. They did not give you any cases where b squared was less than 4ac. Behind the scenes, without you knowing it, they made sure that this never happened. But it could happen in this class. And if it does, it just means that we're going to wind up with these complex solutions. Now, don't be scared. They're not that bad. But we do have to become familiar with the properties of these complex numbers. So first, in general, we'll write all complex numbers like this. We've got a real part and we've got an imaginary part. A and B are both real numbers, but I, of course, is the square root of -1, which is imaginary. Now, this is where it gets interesting. Exponents. If we try to apply exponents to I, you may not get the results that you're expecting. All right, so let's check this out. We'll start with I squared. Now, clearly, I to the first power is just I. You don't have to worry about that. But I squared, now what is this? If I take I squared, what have I done? Oh, wait a minute. You end up with -1. Just like if you had, let's say, radical 2 times radical 2 just equals 2. Okay, so therefore, if I square I just find myself with a real number, which is -1. Now, what happens if I cube I to the third power? Here we go. I can rewrite this as I squared times I, and I squared, we just got through proving, is -1. So I end up with -I. And then how about I to the fourth? That's I squared squared. Now, by the way, this can also be written as I squared times I squared. That probably was a better way to go, but it doesn't matter because you can see this is -1 times -1. So I to the fourth is +1. Interesting. So let's recap that. I to the 1 is I squared is -1. I cubed is -I. And I to the fourth is 1. What happens if I try to go past 4? Let's find out, just for the fun of it. All right, let's do this. I to the fifth can be written as I to the fourth times I. Now, I to the fourth on the previous slide, we just got through seeing is 1. Therefore, this is just I. How about I to the sixth? That's I to the fifth times I. So I've actually got I times I, or I squared, which is -1. Now, I to the seventh is I to the sixth times I, which is -1 times I, or -I. And then finally, I to the eighth is I to the seventh times I, -I times I -I squared, or just 1. Because I squared is -1. That implies that -I squared must be +1. So what this means then, let me just quickly run through this again. So if you notice, it's like they go through a cycle. The first 4 powers are the same as the 5th through the 8th powers. Okay, these are all the same. I to the first and I to the 5th are the same. I squared and I to the 6th are the same. I cubed and I to the 7th are the same. I to the 4th and I to the 8th are the same. So that tells me that I to the 9th would be I to the 10th would be -1, I to the 11th is -I, and finally I to the 12th is +1. It just keeps going through the same cycle. Yes, Fernando.
So wouldn't it be safe to say that after like past four, it repeats? Like you
Yes,
said,
exactly. It just repeats and repeats forever. So you don't ever have to actually calculate the higher order ones. If you need I to the 6th, you say, oh, it's just I squared, which is -1. Now, the thing is, you can't do this on your calculator, of course. It doesn't have this capability, although there might be some calculators that are set up to do this. So for these, you really have to follow the properties. And but I mean, it makes sense. I mean, just if you're just careful with them, you shouldn't have any trouble with this. And really, the thing that starts the whole process is this idea that I squared is -1. After that, they all just fall right into place. But yes, no matter how far out you go, it's always the same 4 repeated over and over and over again. It is a pattern that never fails. That's kind of comforting, don't you think? That's the nice thing about math. Either something is either true or it's false. That's all we have to choose from. Where else in life do you see that? Things are yes or no, black and white, up and down, left and right. There's a nice precision to math that we don't get in many other disciplines. Now, here's an interesting concept. And this might have been something, you may have seen this before, the idea of the so-called complex conjugate. So for any real number, complex number, a plus bi, a minus bi, and a plus bi are considered to be complex conjugates of each other. Now you might say, well, that's nice, but it turns out this can be very helpful in solving problems where we basically want to get rid of the imaginary components of our answer. So for in others, even though imaginary numbers do pop up in equations sometimes, they're not real numbers, so they're not going to help us in the real world. So sometimes we may want to use techniques to eliminate imaginary numbers in our solutions. Okay, so just keep that in mind. This is going to prove to be helpful down the road. But right now, let's just remember that these are considered to be complex conjugates of each other. And here's an example. These two, 3 minus 4i, 3 plus 4i, complex conjugates of each other. Okay. Now, can we perform algebraic operations on complex numbers? Besides squaring, raising I to different powers, yes, we can, as long as we're careful. So let's say we have these two. We can consolidate the real parts into a single expression, and then we can consolidate the imaginary parts. And that holds true for subtraction and addition. Because remember, now just in general, whenever we have real imaginary numbers, we always want to reduce the expression to something nice and simple like this. One real term, one imaginary term. That's what we want. All right, so let's look at some examples. As a matter of fact, why don't we do this? Why don't you tell me, write down on a piece of paper, the sum of these two terms and the difference using the rule we just established. All right, why don't you take a minute and figure out the sum and the difference? All right. I suspect that you're done by now, or just about. So the sum, what are we doing here? We're adding the 3 and the 4 to get 7. And then when we combine the 4 and the -7, we end up with -3i. Now, when we subtract, of course, we have to be doubly careful here because you've got 3 minus 4 for this piece. Here, this is the result of taking 4 minus -7. So you actually end up with -1 plus 11i. All right, so that's because of this negative. All right, now, can we multiply and divide complex numbers? Yes, of course. We can use the distributive property that we know. So let's say this is our complex number. And of course, this is a real number. And literally all you're doing is multiplying this a by b, and the a is being multiplied by the c.
How come you can't multiply it with the I?
Well, I is a constant, so we keep it here. In other words, it's AB plus ACI. So like if you had 3 times 2 plus 4i, you'd end up with 3 times 2 plus 3 times 4 times I. You're basically multiplying the 3 by both of these expressions and then adding them up. This is the distributive property of multiplication over addition. It's like when you have 3 times x plus 2, you end up with 3x plus 6, because you're multiplying 3 times x and 3 times 2 and adding them up. It's just a little trickier with complex numbers, but it's the same property. Let's see, I think there's some examples here. Yeah, like this one. So you're going to have 3 times 2 gives you 6. 3 times -4i gives me -12i. All right, so let's make up another one on the spot. So you got 5 times 4 plus 5 times 7i, and you're done. All right. Now, what if instead of multiplying a constant, a real constant, times a complex number, I now need to multiply, oh my God, 2 complex numbers. Now we're going to use FOIL. Now, this all looks terribly scary. You know what I think we should do? Why don't we just skip directly to an example so you can see how it's not that bad. All right, so let's do this. Here's the product that we're looking for. Now, here's FOIL. So F is -6. O is 27i. The inner one is -14i. And now look at this last one. This is 63i squared, but what does that equal to? Let's go back to our chart. Oh, that's right. I squared is -1. So that means we're going to get some simplification here. And when I bring these together, these two will combine So look what I end up with, minus 69 plus 13i. Now, oh, that turned out rather well. So basically, what this is saying is that if you have two complex numbers and you multiply them together, you can use FOIL, but just be aware that if you end up with any powers of I, you might have simplifications taking place. And so that's why that chart that we had is so helpful for these cases. If I ended up with an I to the fourth power in there somewhere, for example, then we would have reduced it to 1, and that really would have simplified things. So these are very important, as it turns out, because we may end up needing them to simplify our results. All right, I'll tell you what, let me make up another one so we can do it right now. How about 2 plus 4i times minus 1 plus 3i? So what I'd like to do is use FOIL and the properties of I, or the exponents of I, to come up with the result here. Okay. I'll start it just by writing these down. Take it away. All right, let's see how we did. So F would be -2, O is 6i, inner, or I, is -4i, and then last, the challenging one is 12i squared, which is -12, right? So if you forget, I squared would be this. So when you consolidate these, -2, -12, -14, and here we end up with 2i. Okay, now if we can multiply complex numbers, that seems to imply that we should be able to divide, of course. But as always, we do not want to have division by 0. Okay, that's always the constraint on division. But here we have a tool available to us that can help us streamline these division problems. Okay, so let's say we have this case. Now you might look at it and say, oh, you know, it doesn't look like we can do anything with it. But you might be able to simplify it at least by using the following technique. So first of all, I'd remind you what complex conjugates are. I did tell you this would come in handy eventually. The complex conjugate of A plus BI is A minus BI. Now we know that we're allowed to multiply any ratio by 1 without changing its value. The question is, what form of 1 should we use? So our strategy is to do this. We're going to take the original expression and multiply it by the ratio of A minus BI time over A minus BI, because A minus BI is the complex conjugate of the denominator over here, A plus BI. Now you might ask yourself, how is that helping? Because if we apply FOIL to the denominator, we'll end up with a real number. And so the idea here is that you might recall that when we have expressions, we try to avoid having radicals in the denominator. Well, it turns out we also try to avoid having imaginary numbers or complex numbers in the denominator. So this approach is designed to simplify what we have more than anything else. So let's say we do use this expression. And what I'm going to do is just remind you. Now, let's do this. We have A minus BI times A plus BI. If I apply FOIL to that, we have A squared ABI negative ABI and then finally negative B squared I squared. So when I combine these cancel each other out, and I end up with A squared minus B squared I squared, which you see here. But of course, since I squared is -1, this reduces to A squared plus B squared. And that's, of course, a real number. Now, even if this doesn't become a very simple expression, at the very least, we've accomplished our goal of eliminating any imaginary or complex numbers in the denominator. That is by itself enough reason to do this. All right, I'll tell you, let's do an example. It's so much easier with examples. All right, so we're going to take this, multiply so we'll have 4 minus 6i, 4 minus 6i. So we haven't changed anything because this ratio is clearly 1. Then we'll apply FOIL to the numerator and the denominator. So if you apply FOIL to the numerator, now we're not that worried about the numerator, by the way. It can be anything. Okay, here we go. So for the numerator, F will be 20, O will be minus 30i, I will be minus 8i, and L is going to be 12i squared. Okay, so I'll have 20. Now we'll consolidate these two terms. minus 38i. 12i squared is actually minus 12, because remember, this is the same thing as 12 times negative 1. So the numerator reduces very nicely to 8 minus 38i. What about the denominator, though? Let's try that down here somewhere. Of course, I'm running out of space, but I want you to see this. So we'll work out the FOIL. 16 minus 24i plus 24i, negative 36i squared. Now, the key to the whole thing is these two cancel each other out. So you're left with 16 minus 36i squared, which is equal to 16 plus 36, or 52. Yes, Fernando.
Since you said that those two cancel each other out, is it because not only they have the same variable, which is I, which is the constant, but
right,
it's a negative and a positive? So
that's right. Exactly. In other words, it's negative something positive something add up to 0.
Oh, okay.
They're the same thing with different signs. Okay, they're identical to each other except for the sign, so therefore they cancel each other out. They add up to 0, in other words.
But if they didn't have the constant, then it would be different, right?
Yeah, then you might get a sum like 2i or 8i or whatever, but because they're the same, they do in fact add up to 0.
Oh, okay.
That's why. So that's why we're doing this approach, because you can see this is, you know, it's got the imaginary numbers in the denominator, which we don't want. This one does not. Okay, so this is a little bit simpler to work with. And so the point of this is that you're not so much changing it, you're just simplifying it. All right, now, okay. Oh my God, there's a typo in the notes. I just noticed it. Oh, this in the notes, it's got 60 here. It should have, oh boy. This is 52. So I'll fix that. Make a note to myself. But yeah, those two should have been 52. Okay, so now, what else can we do with this stuff? Oh, here's a good idea. Let's say that for some reason we have a function like f of x equals 3x squared minus 2x plus 7. And you know how to evaluate this. Let's say if I wanted to know what this function is equal to when x equals 2, what would I do? I would literally replace all the 2's in the equation, all the x's with 2's. And we've done that before. And it'll show you a particular point on that function. But there's nothing to stop us from substituting complex numbers into this function if there's some reason for it. So basically the technique would be exactly the same. You would take whatever your expression is and plug it in and replace all of the x's with that complex function, and you'd end up with some kind of an answer that contains imaginary numbers. But you know, if that's what you're after, that's how this would work. So I'll tell you what, this is a fairly complicated equation. So I think it's time that we can have our break right now. We're getting into some very deep water here. So why don't we stop right here? And when we get back, we'll go through this one step by step so you can see exactly how this works. And along the way, we'll get some review with some important properties of the complex numbers. And but when we're done, we'll have a relatively simple expression. But it's important to be aware that you can substitute complex numbers into real functions like this. All right. So, all right, we'll knock it off for a bit here. And when we get back, we'll pick it up with this discussion about the properties of complex numbers. And then we can move into the other types of functions that we wanted to look at, like, for example, polynomial functions and rational functions and all these other ones that are very important in practice. Okay. Yes, we can have a nice little break. Let's come back. And by the way, yes, the Genius Scan is the one that I couldn't remember before, but there's others too. As long as it's a scanning software on your phone, check it out just to see how well it works. I seem to remember that people, when they sent it to me, the quality was quite good, although I personally never used it myself. And so, yeah, we can come back around 10. That should be enough, 10-ish. So if you need to do something, go do it now. And then when we get back, we'll get back into this, okay? All right, see you all in a while.
Wait, Professor.
All right, I guess that was a long enough break. So we'll start up again here with evaluating complex functions. So here's what we're going to do. We'll start by evaluating this. Actually, let me do this on a separate slide, just so you can see all the steps. So we've got f of x equals 3x squared minus 2x plus 7. And suppose I wanted to know what that value would be when x equals 8 minus I. Now, of course, I can't draw this on a traditional XY coordinate system because it does not show complex numbers, but we can still come up with a value. So f of 8 minus I, and again, the whole idea here is that you're simply replacing all the x's with 8 minus I. Now, the only tricky part here is this square here, 8 minus I squared. So why don't we do this? Let's take a detour and use FOIL to figure out 8 minus I squared. Then we'll plug it back in here and we'll take care of the rest of this expression. So that's what we're looking at, F-O-I-L. F is 64. O is minus 8I. I is also minus 8I. And then when we square these two i's, well, we know what's going to happen there. We're going to have 64 minus 16I plus I squared. But remember, I squared is -1. So we end up with 63 minus 16I. Now that goes back up here into the square term. So let me do this. Let's see, I think we can write it all over again. I thought I might be able to copy it, but that's okay. So remember, this is what we're starting out with. And we know that this piece, we just got through showing that this is 63 minus 16I. So let's write it like that. Now we'll simply use the distributive property to take care of these first two terms. Here I've got 3 times 63 and 3 times negative 16I. So it's 189 minus 48I. And here, of course, I have minus 2 times 8 and minus 2 times minus I, which is plus 2I plus 7. So now, of course, we'll just gather up all the constants. 189 minus 16 plus 7 is 180. And we'll gather together the I terms minus 46I. And that's our final result. Okay, so all we did was substitute a complex number into this quadratic equation, and we end up with, of course, a complex result. There's nothing to prevent us from doing this. It's just that the result will also be a complex number. All right, now I did it here as well, if you want to go through it one more time. Now, how about this one? Oh, let's go back and make sure you're all caught up. And then we'll go on to the next one. All right, so it wasn't that bad. How about this one? Let's evaluate it. Now, this is a straightforward one because you're just replacing all the x's with 10i. So look how easy this is. But you know what? We're not done with it, are we? No, because we still have a complex number in the denominator, which means that we're going to do one more step, and that is multiply by the complex conjugate. Let's not forget about that little detail. Remember, we're trying to avoid having complex numbers in the denominator. So let's try this. That would mean I'm multiplying the complex conjugate of this denominator is 3 minus 10i. So we'll have that in the numerator and the denominator. So now we're going to have to apply FOIL to both the numerator and the denominator. So just because I'm sure you could use the practice, why don't you take a minute and come up with a solution for this using FOIL in the numerator and the denominator. All right, I'll give you a couple of minutes and let's see what you can do. Let's see how this went. So for the numerator, we'll do this up here. You're multiplying 2 plus 10i times 3 minus 10i. And so when you do FOIL, you have 6 minus 20i, 30i, and minus 100i squared. When you consolidate those, you'll have 6. Now, these two don't cancel each other out, but they do combine to give us 10i. And of course, we know what's happening here. I squared is -1. Which means you actually are adding 100 here. So you end up with 106 plus 10i. That's our numerator. Now for the denominator, Remember, in the denominator, this was designed to simplify our result. And in fact, it should end up being a constant, a real constant, that is. Let's check it out. So we've got 9 minus 30i plus 30i. And then finally, again, we have minus 100i squared. So these do, in fact, cancel each other out. 9 minus 100i squared. 9 minus 100 times negative 1. 9 plus 100. So the final result is 106 plus 10i, all divided by 109. And again, it's not like really simple, but at least we don't have that pesky complex number in the denominator. This is what we're trying to avoid. This is the final result. All right, so hopefully you got that. Oh, and by the way, one more thing. Sometimes you see it written like this. I like this, the way it's written, but sometimes in some books, they'll split it up into two pieces. It was originally, the way we got it, we got 106 plus 10i over 109. Because remember, a complex number is typically written as a plus bi. So some books will split this up into two pieces just to stay in that form. But I would say this is fine right here. But yes, if you must have it in this form, this is what it would look like. All right, so I think we're now in pretty good shape with complex and imaginary numbers. I think we understand them well enough to carry on. Given it, now we're not going to see a whole lot of them going forward. We will see them from time to time, but we're not going to focus on them. In a different kind of class, you might use them more often, but not so much here. We're trying to focus on more practical applications, and especially in areas like finance and economics. You're not likely to run into these. In areas like engineering and physics, you might run into them. Not so much in more, let's say, down-to-earth applications. They're not so theoretical. But anyway, so the next function, which you're very familiar with, is our old friend, the quadratic function. And this is what it looks like. And the reason why it's called quadratic is because it has that x squared term. All right, now a quadratic function typically will look like either this or possibly this. This type of graph is called you might recall, a parabola. And so whether it's facing up or down depends on the sign of A. Over here, A is positive. Over here, A is negative. By the way, A can't be 0, because if it is, we just wind up with a linear equation. So we're assuming that A is not 0. So if it's positive, we have an upward-facing parabola. If it's negative, we have a downward-facing parabola. Now, another thing we want to note here is that it crosses the horizontal axis in two places. Because of that x squared term, those are solutions of the equation. Okay, the value of x at both of these points are the solutions of the equation. So what we want to know is, how do we solve for a quadratic function? All right, well, there's a couple of things we could do. And one of them you're very familiar with, it, which we saw earlier, the quadratic formula. That's what it's meant for. So, and again, if you have an x squared term in your function, we call it quadratic, or sometimes it's called degree 2. All right, you might recall that convention. Degree is the highest exponent in the equation. Or function. Okay, so quadratic has degree 2. So something like this. If you move it up to one step, f of x equals ax cubed plus bx squared plus cx plus d. Well, it should be pretty clear that this is degree 3, and this is also what we know as a cubic equation. Here's quadratic, and here's the cubic one. And they all have names. You know, after a while they get a little awkward, like what is x to the 5th? It's something like quintic or something ridiculous like that. So we often end up referring to them by their degree rather than giving them a name. Okay, now of course, as I started to say, these quadratic functions are always expressible as a parabola or illustrated by a parabola. And, you know, we're pretty familiar with a parabola. It has two very key properties. It looks like a U and it's symmetrical. Let's say this is our parabola. Everything on this side matches up everything on this side. That's what the word symmetrical actually means. The left and the right-hand sides. And the right-hand side are, let's say, mirror images of each other. Okay. And I mentioned as well, you recall that when a is positive, the parabola faces up. This would be an example, 3x squared plus 2x plus 1. Of course, a is 3, which is positive. It's not a perfect graph, as you can see. This is Excel. It's just okay for graphs. Here's another one. When a is negative, the parabola faces downward, as in this case. And of course, here a is negative 3, which is negative. Very nice. And like I said, too, if a equals 0, then this becomes a simple linear equation. So it's no longer a quadratic function. All right, now we're going to take a step back here and actually take a closer look at parabolas. They're actually more interesting than we generally realize. They have several key properties that we want to understand. So we're going to do that. We're going to take a magnifying glass, I guess, and focus our attention on parabolas for a few minutes, just to get a better feel for some of the most important properties of these parabolas. Now, it turns out that a parabola can be defined by 4 different characteristics. Okay, now some of these you've heard of, some of them you haven't. So there's 4 ways in which we can characterize a parabola, and we're going to see how each one of them works. So in all cases, the equations we'll be deriving are based on this expression for a quadratic function, ax squared plus bx equals c. So it's understood that a is the coefficient for x squared, b is the coefficient for x, and c is the constant. Now, vertex, what does that word even mean? Interesting question. It's not one of those words that you often run into in the real world. Well, think about it this way. If we have an upward sloping or upward facing parabola, the vertex is the minimum point. If we have a downward sloping parabola, this is the vertex. So basically think of it as the minimum or maximum point Okay, and of course, once again, just a quick reminder, this implies that A is positive and that A is negative. Now, the question is, how do we identify it? And by the way, I do want to point out, the way I've been drawing these parabolas, it looks like they always have their vertex on the vertical axis. It doesn't have to work that way. Let me show you a couple of other examples. There's nothing to stop our parabola from looking like this, for example. And then this would be our vertex, and it's not on the vertical axis. And then we could have something like this. Okay, well, I didn't draw that one terribly well, but I wanted just to make sure it's clear that the vertex doesn't have to be in the vertical axis. It can be anywhere. All right, so let's see. Now, a quadratic function, now this is, it turns out, just like, remember we discussed that with a straight line, there's two different ways of writing it. Let me just quickly review that with you. A line or linear function can be expressed as, so the traditional approach is y equals mx plus b, which is sometimes called the slope-intercept form. But we also have y minus y1 equals mx minus x1. Okay, let me make these into subscripts. And that, as you know, is the point slope form. So something similar to that is happening with quadratic functions. All right. So we have the traditional f of x equals ax squared plus bx plus c. But for some applications, it's more convenient to write it in the second form, where the point h comma k is the vertex of the function. I don't know if there's a separate name for this expression, but both of these actually end up meaning the same thing. So in other words, there's two different ways of expressing it. For some applications, this actually proves to be more convenient. So we want to familiarize ourselves with this new way of expressing quadratic functions. So let's take a look at this one. All right, so clearly, this is the traditional form for a quadratic function. A is 2, B is -6, C is 7. And the picture, as you can see, since A is positive, it will be facing up, we'll call it. The question is, where is the vertex? All right, so here's the Excel version. Yeah, it's down here somewhere. It's, like I said, it's kind of tough. You know what, let's do this. Let's switch over to Symbolab. I want you to be able to see it. Symbolab explicitly identifies, hold on. All right, so I want to get a graph of this. Y equals 2x squared minus 6x plus 7. Whoops. All right, so let's take a look at this thing. All right, now here it's crystal clear. This point, 3/2, comma, 5/2 is our vertex. because it is the smallest value on this parabola. So let's make a note of this. 3/2, 5/2. We're going to see now where these came from. So this is H and this is K. All right, that's what this is all about. The first number is H, the second number is K. So here's what we're going to do. We're going to try to rewrite this. The original function was this. We're going to write it in the following format. Now, it turns out that there's a formula for H. So, right off the bat, that helps a lot. H is equal to negative b over 2a. So now remember, the original function was 2x squared minus 6x plus 7, which implies that a is 2, b is negative 6, c is 7. So therefore, you can see we just plugged in b over 2a. Oh, there you go. There's the 3/2. Now, we already knew this, but now we know where it came from. So what about the k part? How do we know that k is 5/2? Well, that's the easy part, because what you're doing is this. Once you know the 3/2, k is just the original function evaluated at h. Okay, so remember, f of x is 2x squared minus 6x plus 7. H is 3/2, sorry. So therefore, k is f of 3/2, 2 times 3/2 squared minus 6 times 3/2 plus 7. And you can see then I've done that down here already, and then I evaluated it, and I ended up with 5/2. So we know that h is 3/2, k is 5/2, and that just confirms what Symbolab told us. But now we'd like to write this in that special form. Okay, and what would that give us? Let's find out. Give you a second to catch up, and then we'll show you how that works. All right, here we go. Given that we're trying to create this function, now remember the original function, once again, I'll just remind you, 2x squared minus 6x plus 7, therefore a is 2. We need a for this. And h, we've already determined is 3/2, and we know that k is 5/2, so this is the final result. So if I were to go to Symbolab and type that in instead of what I had in the first place, you'll see it'll give me the same result. Okay, in fact, maybe we'll check it out. So let's change this to two times x minus 3/2 squared plus 5/2. And we'll say, oh, please, Symbolab, show us another graph. It's the same. Of course it is. So that means that they both represent the same information, but expressed in a slightly different way. Okay. Very good. Now, remember I said there's several features that formally identify or uniquely characterize a parabola. We now turn to the axis of symmetry. Now, remember we said that symmetry means that the two halves of something are mirror images of each other. Think of the axis of symmetry as a line, the line around which the symmetry takes place. So in other words, imagine that we had a parabola that looks like this. And here's the vertex. This line is the axis of symmetry. Because now you can see everything on the left and the right are the same. And we can calculate the value with this formula based on A and B. Now, I just want to remind you that when you have a function like this, let's say you're on the XY coordinate system. If you have something like this, this is a vertical line because the Y never changes. I mean, sorry, the X never changes. So this is technically not a function. If you remember our discussion in the beginning of the semester, it fails the vertical line test, of course. Or think of it this way, multiple Y's are being associated with the same X. So we can't have that. But what it is a vertical line. The slope is undefined. And it's not a function. So the axis of symmetry is a vertical line. And it's the vertical line that cuts through the vertex of this parabola. So it's a very straightforward idea because if you look at it carefully, you might recall that we saw earlier H is minus B over 2A. So basically what all you're doing is you're finding the vertex and then you're drawing a straight line through it, a vertical line, because H and X are the same number. Okay, except that H represents the X coordinate of a point. This X is the straight line, a vertical line. So it's no coincidence that these are the same thing. You're basically just drawing a line, a vertical line through the vertex. That is your axis of symmetry. And again, it's the line around which the symmetry occurs because the left side and the right side are mirror images of each other. So this isn't really even a separate formula. Okay, well, that helps. Less formulas is better, I think you'll agree. So remember before we found that H comma K was 3/2 and 5/2. So it should come as no surprise to you that the axis of symmetry is just that line. There it is. Okay, so it's just obviously directly related to the vertex. Now, the third part, which you're very familiar with, the third identifying feature of a parabola are the so-called solutions, or sometimes they're called zeros, or even sometimes they're called roots. And all that means is where does the parabola cross the horizontal axis? And of course, we can see there are two of them. All right, except, now there is an exception. Let me show you this. Now, first, here's our friend, the quadratic formula. Everybody knows this from high school. And what this means then is that you're identifying the 2 points. Let's call this x1, 0 and x2, 0. this formula is giving us both of these x's. You can tell there's two solutions because of this plus and minus symbol. But I do want to remind you, if we have a parabola that looks like this, let's say, oops. If the parabola does not cross the horizontal axis, then the solutions are imaginary. And that would show up in the quadratic formula, as I mentioned earlier. You would end up with b squared is less than or AC, so that, and you would end up with the square root of a negative number. And that's how you would know you have imaginary solutions, and that the graph of this parabola does not touch or cross the horizontal axis. Okay, so in other words, if this term is negative, then you'll end up with imaginary solutions. And that would again indicate that the parabola itself does not touch or cross the horizontal axis. Okay, so for the most part, we'll just stick with cases where this isn't happening, but just be aware that this is a possibility. All right, now, by the way, here's a side note, this is just for your interest. It turns out that the axis of symmetry is the average of the two solutions. In other words, in a case like this, here's the vertex. This becomes the axis of symmetry right here. These are the two solutions. And what they're saying is that the axis of symmetry, whatever it is the average of x1 and x2. So in principle, you could calculate it if you wanted to by looking at the two solutions and averaging them out. Well, that's interesting. Okay, well, anyway, so that's just a fun side note. Let's do this. Now, here's our first quadratic equation. We're setting this function equal to 0. In fact, let's take a look at it in Symbolab. And so you'll be able to visually see right away what's going on. What is it? 3x squared minus 3x minus 4. So we'll graph this, and we'll be able to see from the graph what the solutions are. All right, one of them is -1, okay, and the other one is +4. All right, so we know in advance that the solutions are -1, just by looking at the graph. Well, let's prove it. Let's use the quadratic equation. So here, remember, because the function is written as ax squared plus bx plus c. By the way, here, x squared, as you know, is the same as 1x squared. So here, a equals 1. Okay, so a is 1. B is clearly -3, and c is -4. So that in mind, we can plug these into this quadratic formula. In fact, let's do this. Now, I know you all recognize this from high school. Now it's just a question of evaluating it. Okay, so I'm just, this information is right on top. I'm just moving to the next slide. This is what we just did. So now you can go through the steps and you can see, for example, this becomes +3. Now let's see what's going on inside the parentheses, or under the square root sign, I should say. -3 squared is clearly 9. -4 times 1 times -4 is +16. The denominator is 2. So you've got 3 plus or minus radical 25 over 2, which is the same thing as saying 3 minus 5 and 3 plus 5. So this plus and minus means first subtract, then add. So you'll have two different numbers. This first term is -2/2. This is 8/2, which reduces to, what a surprise, -1 and 4, just like we saw on the Symbolab graph. Oh, so that was pretty straightforward. I think you'll agree. Okay, so that's a classic example of how to find the solutions of a quadratic expression. All right. And of course, what that means is that it crosses the axes, the horizontal axis, I should say, as we saw with Symbolab. At these 2 points. And those are the solutions. So in other words, imagine that this was a function that tells us how much it costs to produce a product. We can use that information, as it turns out, to figure out the point at which we can minimize our costs. So, there's a lot of potential applications with these equations in practice. But now let's try this one. So what I'd like you to do to get some more practice is plug these in and solve for the two values of x. And then we'll throw this into Symbolab and see what it looks like. All right, so once you give that, take a shot at that and see what you get. All right, let's see how we did. All right, so we have to be careful of the negatives. The most common problem I notice when people use this formula is with the negatives. It's so easy to forget about all these different negatives. And so remember, here we have -6, which makes that +6. And then over here we have -6² minus 4ac all over 2a. This is 36 minus 32. Down here we have 2. So it's 6 plus or minus the square root of 4 over 2, which of course is just 6 plus or minus 2 over 2. And when you break it up into two pieces, you've got 4 halves and 8 halves, which of course reduces very nicely to 2 and 4. All right, let's see what this looks like in Symbolab. Okay, this is the graph, and it's a upward-facing parabola, of course, but it crosses at the points 2, 0 and 4, 0. Now you notice the vertex is not on the vertical axis; it's over here. This is our vertex. If we were asked for that, it would be 3, -1. But here's what we were saying before: the average of 2 and 4 is 3. So of course the vertex has to be where x equals 3. We can figure out what y is by plugging 3 into the quadratic equation. It's just basically the halfway point between the two solutions. That's because the parabola itself is symmetrical. And the point of symmetry is this axis, which takes place at the vertex. All right, now, so this is pretty straightforward. Oh, here's a fun question. A carpenter is building a rectangular picnic table. Due to space restrictions, the length must be 2 feet more than the width. All right, let's visualize this thing. So let's say that width is x, length is x plus 2, because the length is 2 more than the width, and we need to build a table whose area is 35 square feet. The area, as you recall, is the length times the width, which in this case would be x plus 2 times x, or x squared plus 2x. Now, this is required to equal 35. So if you make a slight change in this equation by subtracting 35 from both sides, this is your result. This equation will tell us how many feet the length should be and how many feet the width should be. The only issue here is that there's going to be two solutions. So let's see how that works out. So basically what you're being asked to do here is solve this quadratic equation. Okay, so let me sneak down here and remind you that this is x squared plus 2x minus 35 equals 0. So that means that a is 1, b is 2, c is -35. Now you plug in these numbers. That -35 looks pretty scary, doesn't it? Okay, but when you do all the work, you'll see we have -2 plus or minus the square root of 144 over 2. Now, 144 is a perfect square. It's just 12. So I end up with -2 minus 12 over 2, comma, -2 plus 12 over 2. And so I've got -14 halves, 10 halves, or -7 and +5. All right, so let's quickly look at this in Symbolab. X squared plus 2x minus 35 equals 0. Okay, There we go. -7, +5. That's what we found. Now, because though of this application, we're looking for the dimensions of a table. And clearly, it's not possible for the width to be negative. Therefore, the correct solution is 5. So in other words, let's draw the picture again. So if x is 5, that means the width is 5 and the length is 7. Does that work? Yes, it does. We have our requirements satisfied. The length is clearly 2 feet longer than the width. And on top of that, the area equals 35, just as we require. That was kind of fun. But it points out here that in certain types of applications, we can't have these negative solutions. And of course, if we had a complex solution, we would have had to toss it as well. So the answer here is that x is 5, meaning that we're building a 7x5 table. How about that? All right, now there was a fourth property of parabolas that we need to analyze. Let's go back and revisit the list. Here we go. The vertex, which we know is that point at which either the function is minimized or maximized. The axis of symmetry is that straight line through the vertex that divides the parabola into 2 equal halves. The zeros or solutions are the points where we cross the x-axis. The y-intercept, that's a different question. Like here, for example, the y-intercept would be right here. Where does it cross the vertical axis? Now, it has to cross somewhere. Okay, these parabolas go on forever. It's not possible for them to miss the y-axis. So how exactly do we find this? Well, of course, there's a formula. There's always a formula. What you're going to do, and it's so simple, it's almost ridiculous, is find the value of this parabola when x equals 0. Okay, so in other words, all you have to do is replace all those x's with zeros. And in fact, it's just the constant. Okay. Wow, that's easy. So like here, it would be -35. Okay. And now if you look at the equation though, that should be no shocker to us because that's the -35 right there. So C is the vertical intercept. And so that one is nice and easy. We like easy ones, don't we? Yes, we do. All right, now, as always, whenever we introduce a new function of some kind, we want to know what are the domain and the range. Now, let's go back and look at this one. Usually Symbolab mentions it. The domain here is all real numbers. Now, remember what the domain is. The domain is what values of x can be plugged into this formula. There's no value of x that would lead to division by 0 or a negative square root. But what about the y's? What about the range? Well, you can plainly see the range starts here. The global minimum, as it's called, or the vertex, represents the boundary for y. So in this case, the range is actually everything from -36 up to +infinity. And there it is right there. The question is, how do we find that out? Good question. Well, again, remember, this is coming from the vertex. Here we didn't actually calculate the vertex. Oh, yes, we did. Symbolab very kindly found the vertex for us -1 comma -36. So think of this as the limiting point, depending on whether the curve faces up or down. Now here, they're giving us two possible equations for the range. But keep in mind, remember, this itself is just h in the vertex. Okay, so, and f of h is k. All right, remember that? So h is minus b over 2a. F of h is k. So basically, this is the x coordinate. I'm sorry, y coordinate of the vertex. That's if the function, if the parabola is facing up, by the way. If it's not, then it works the other way around. Okay, this becomes the k. And we end up having something like this. So there's the range would be everything from this point down. All right, so let's look at an example. And we can prove it with Symbolab. So we start with this function, f of x equals minus 5x squared plus 9x minus 1. Now, we're guaranteed, we don't have to worry about this. The domain is just automatically negative to positive infinity. The question is, what about the range? Now, first things first, this clearly faces downward because a is negative. So remember, a is -5, b is 9, and c is -1. So we know we have this case. So let's go look at Symbolab, just so we can visualize it better. Minus 5x squared plus 9x minus 1. Let's see what that picture looks like. Okay, so this is what we would expect. All right, and here's our vertex. Ooh, those are some not pleasant numbers. 9/10 and -61 over 20. So that means that y can never go above 61 over 20. It's everything from 61/20 down to negative infinity. But keep in mind, this 61/20 is k from the vertex. Remember, the vertex is hk. This is just k. And remember how k was calculated. K is f of h, where h is negative b over 2a, which in this case is 9/10. And then k, we'll do it up here, is f of 9/10 minus 5 times 9/10 squared plus 9x minus 1. Ooh, that's a messy one. Let me get this out of here. Minus 5 times 81/100 plus 81/100. Oh, sorry, 81/10 minus 1. All right, well, you know what, I'm getting terribly low in space here, but let's see, let's turn these all into 100s. And so we'll have minus 405/100 plus 810/100 minus 100/100. Ooh, boy, this is a tough one. So minus 405 plus 810 minus 100 is 305 over 100. which if you divide the numerator and the denominator by 5, you'll get 61 over 20. And that's what Symbol Lab had, right? 61, yeah, there it is. So yeah, we did it correctly. 9/10 and 61/20. So H is 9/10, K is 61/20. So basically the range is, like I said, from 61/20 down to negative infinity, or in interval form, and by the way, that includes the 61 over 20. That's why there's a square bracket here. It includes f of negative b over 2a, which again is just k from the vertex. All right, so that worked nicely. All right, so here I went through all the gruesome details, and yes, that's correct. Oh, one thing, no, here's a tiny little problem. Okay, yeah, I better fix that. That's all right, so now, God, what comes next after all of that? That seemed like a lot of work, didn't it? Now, this was 3A, by the way. We're done with 3A. And actually, let me quickly save this. What is today, the 22nd?
Yes, sir. Today's the 22nd.
Okay, yes, good. The rest of this discussion, the other functions that we want to consider are, I split them up into something called 3B because, you know, I wanted to keep them apart from each other. And because this is very, very long. So that one's done. So I'll put it aside and go get 3B. There it is. All right, let's get this baby open. Now, remember in the beginning of 3A, we mentioned, here it comes, that we have several different functions to look at here, several different kinds of functions. So let's go back to the list. So we've reviewed complex numbers and we've reviewed quadratic functions. So we saved these three for last, and we're going to look at their properties. And by the way, what comes in chapter 4 is we're going to save them for a special separate chapter. We're going to see what are called exponential and logarithmic functions. Okay, so here we're focusing on these, which are basically simple extensions of what we've been doing. So, all right, so we'll go now to polynomial functions. Word polynomial means many numbers. That's really what it actually means. And sometimes, in fact, you know what, let's do this. There we go. Okay, two diverse roots, the Greek poly meaning many and the Latin nomen or names. Okay, it's many names, but it's usually interpreted to mean many terms. Okay, it was derived from the term binomial by replacing the Latin root bi with poly. Yeah, nomial usually means, I know it technically means name, but it's usually interpreted to mean terms in an expression. So it just means there's many terms. That's literally all that it means. So now here, oh my God, look at this. What they're telling us here is that we can have any degree we like. So remember, a linear function looks like this. Just a quick reminder. The only x we have here has an exponent of 1, which means we call this a function of degree 1 a quadratic function has an x squared term in it, and that's why it's called degree 2, because we have a square in here. And then the third degree, the cubic function, is this one. And it just means there's a degree, one of the terms at least has x cubed in it. This expression, this catastrophically complex expression, means that this is an nth degree function. And it's just a general way of showing that any of these are possible. We can have a 4th degree, we can have a 5th degree, we can have a 100th degree, but this is the general expression. And when we get up into this area, these are all referred to as polynomials. Technically, a linear function is a polynomial, but we usually reserve it for the higher order ones. So here we are. So we've got a coefficient and an exponent of n. Then we go to the next lower one, n minus 1. We always write these in descending order of exponents, so that when we get to the end, we have a constant. So we're going to use the one that we need. The only constraint is that this one cannot be 0. Okay, so like when we have a quadratic equation, we saw that a cannot be 0. So the highest order coefficient can never be 0. Other than that, anything goes. Very good. So that's just meant to show you what polynomials look like. We're going to focus on a handful of specific cases. Now, by the way, there's one more thing I want you to notice. I forgot all about this. N is a non-negative integer. Now, the word non-negative means that it's either greater than or equal to 0. In other words, a number that's non-negative is either positive or equal to 0. Strictly negative, strictly positive means that it does not allow for 0. And then we have the same idea down here, non-positive. Okay, it can be 0 or negative, and then negative x is negative, strictly negative. So what we're saying here is that in order to qualify as a polynomial, the n's have to be not only integers, although they can be zeros, they cannot be negative. And because they're integers, they also can't be fractions. So we're restricted to numbers like 0, 1, 2, 3, 4, 5, 6, 7, et cetera, et cetera. If you see a negative exponent or a fractional exponent, then it no longer qualifies as a polynomial. It is something different. All right, so just remember that. So in fact, we're going to have a little quiz right now. Which of the following qualify as polynomials? Well, the first one is fine. Each n is a non-negative integer. And when I say n, I mean exponent. I guess that's what I should have said.
Is the last one fine?
No, the last one is not fine.
Oh, wait, never mind. I see it. My bad. Whoops.
You're right. The first two are okay. Whoops. Yes, you're absolutely correct. This one is not. So these are polynomials. Not so this one. And you're absolutely correct. because you'll notice one of the exponents is -2, and that blows the whole thing up because that's not a positive or non-negative integer. Okay. It's a different kind of function. We'll get into that later on, but it's not considered to be a polynomial. -2 is not a non-negative integer. So that one is a no. All right, and that's all you have to pay attention to. And if you get something weird like this, 1 over x is no, because this is x to the -1 power. Okay, I just want to throw that in there as well so you can see that. All right, great. So once we got that, and it goes through it here, each exponent is a non-negative integer. Those two are fine, not this one. It doesn't belong to the club, so to speak. The degree, as we've already mentioned a few times, is the highest exponent in the function. Okay, and that's also a reason why we like to write these with the highest exponent first, so that it's clear right away. This is a degree 4 expression or function. This one is of degree 7, and this one is of degree 5. And by the way, the sign of the coefficients does not get involved in this at all. It's all about the exponent. So like here, we have a -8, but that doesn't matter. It's still degree 5. All right, so there we go. So now we understand what degree means. And we have another term we need to know. It's called, and it's a very simple idea. Just a quick reminder, when we have an expression like this, 5 is called the coefficient. X is the base, and 4 is the exponent. So yeah, we're about to define a word that involves coefficients. So given how we determine the leading, say the degree, there's also this concept called the leading coefficient. And that is simply the coefficient of the term with the largest exponent. So if you had this, oh, whoops, no, sorry. 7x squared is what I wanted to do. So this becomes the leading coefficient. It's a very simple idea. Because this is a degree 4 polynomial, we find the leading coefficient in this term. And that's all there is to it. The leading coefficient is simply the coefficient of the term with the highest exponent. Okay. So let's look at a couple of examples. So here, for example, the leading coefficient is clearly the 5. And here it is just the 9. So it's very nice and easy. If only the rest of it was this simple. Wouldn't we be happy? Yes. And then, of course, down here, this last one, the leading coefficient is -8. Nice. Okay, here we go. Dividing polynomials. Okay, now this is a bit of a mess. You've done this before, but it's possibly been a while. Can you divide polynomials? Yes. As long as you do not, of course, divide by 0, but it's a very cumbersome process. Now, there are programs. I'm not sure if Symbolab is able to do this. I'd like to try it though. Normally, when you do a division like this, let's say, for example, you take 27 and divide by 4. Well, clearly 27 is not divisible by 4, but what you can do is write this as 6 plus 3/4 because 6 is 24 over 4. So therefore 27 over 4 equals 24 over 4 plus 3 over 4, or 6 plus 3/4. This number is called the remainder. This is the quotient. And this is the remainder. You might remember that was such a long time ago that you did this. Normally we don't bother. I mean, 27/4 is probably cleaner than 6 plus 3/4, but you might remember when you first were learning about division that you were taught how to do this. And exactly how is that done? Oh, I'm going to show you a graphical technique and you're going to say, oh my God, is that right? Okay. Let me remind you how you might have done this. 27 divided by 4. All right, how did that work? Oh my God, how long has that been? Now, in a simple case like this, you would see that 6 is the largest number that evenly divides. And now you cannot divide 3 by 4, so you would end up with 6 plus 3 over 4. Or how about this one? How about dividing 7 into 1032? You'd put a 1 here, subtract 7, drop down the 3. Now 7 goes into 33 4 times. And you're left with 5, bring down the 2, and then you'll have a 7, and you have 3. So 7 equals 1032. Can be written as 147 plus sorry, this is what I'm aiming for. Yeah, that's better. Okay, that's good. Or alternatively, you can write this as 1032 equals 147 times 7 plus 3. And so if you're going to do it like that, we have some formal terms here that we need. This is the dividend. Now, I don't expect you to memorize these. This is the divisor. This is what we're using to divide the number by. This is what we're going to call the quotient. And this 3 is, of course, the remainder. Now, we can do something just like this with polynomials. And sometimes we get a remainder, sometimes we don't. The question is, how in the world do you divide one polynomial by another? Now, you may have seen this before. So let's try this one. And I'm going to see if it would be very nice if Symbolab can do this for us, because it is kind of a headache. So let's try this. Let me show you how this was done. Okay, so what we're doing is we're taking f of x is 2x cubed minus 3x squared plus 4x plus 5. And we're dividing it by x plus 2. So we're going to use the same setup. Okay, so what value when multiplied by x plus 2 will give us 2x cubed? How about 2x squared? If I multiply this x plus 2 by 2x squared, I'll get 2x cubed plus 2x squared. What I'd like to do now is subtract this entire expression. You have to really watch the signs though, because these will cancel. This term becomes negative, and I end up with minus 5x squared. And then I bring down the 4x. Now what do I need? Let's try minus 5x, because that's going to give me minus 5x squared minus 10x. When I multiply this by this, if I subtract this, this becomes positive, so that these can cancel out. This also becomes positive. Now I can still squeeze out a 7 here. And when I subtract, I'm going to wind up with minus 9. Okay, now I hope I did that right, because I'm looking at my answers here and I'm not seeing the same answer. Uh-oh, I hope I didn't goof it up. I'll tell you what, let's check with Symbolab. Now, the problem with Symbolab is even if it can do this, it might give us a very messy polynomial that looks like this. But we have to figure out. All right, let's try this. I have my fingers crossed here. 2x cubed minus 3x squared plus 4x plus 5. Let's see what happens when it divides that by x plus 2. You notice it's thinking. And it's not happy, I can tell. Oh boy, we may have, wait a minute. Oh, I'm so disappointed. It didn't actually create a solution for us. All it did was graph it and find the intercepts and all the rest. I thought it might do the algebra, but I don't think so. Oh, that's so disappointing. Yeah, I mean, this is a nice product, but it's not exactly top of the line. By the way, I accidentally found out the other day that if you're interested, there's a software product called Mathematica, and it's produced by a company called Wolfram. And think of it as a like Symbolab raised to the 10th power as far as its power and ability go. Here's the interesting part. Because you're at SUNY Purchase, you are able to get a copy of Mathematica for free. All schools do this. They all have a bunch of software that they've made deals with a software company. The thing is, Mathematica is happy to do this. I'll tell you why. Because first of all, the license expires when you graduate. And secondly, if you start getting used to using it in school and you go out in the job market and start using math on your job, you may want to use Mathematica. And in fact, your company may buy it just for that reason. So they're hoping to turn you into future customers. And so you can get SPSS, which is a statistical package. And now Final Cut, God, I don't even know what that is. I thought that was like a video software thing. Does anyone know what Final Cut is? Oh, okay. Let's see. Let's just quickly check that out. They probably also have Office. It doesn't specifically say that. Most schools also offer Office. Yeah, that's what I figured. It's a video editing software. And it's free as long as you're in school. But if you feel like, if you're a math major in particular, and you feel like the Symbolab is helping you, you can download Mathematica and get to the next level where it really can do anything you want, really. Like this would be no problem for Mathematica. It would give you the answer just like that because it's that sophisticated, but it takes a while to learn how to use it. That would be the only trade-off. So I just wanted you to be aware that I didn't realize this myself until I got an email from them one day and said, listen, do you want Mathematica? I guess they looked at they looked up a list of all the professors who teach math and sent us an email and said, by the way, we have this wonderful software product waiting for you. Why don't you download it? Yes. Oh, right. You're right, Alex. So yes, I thought so. I wasn't sure. It's for video. I personally do not take videos. I use I do take a lot of pictures, but I don't use software, so I don't really need this thing. But if you do, if you're a big video maker, this would be a great way to edit your work and make it look more professional. And it's free. The real thing probably is very expensive. Very expensive. I have a lot of performing arts majors in my other classes who might be interested in this. I guess here, mostly you're either math majors or computer science majors or something not in the performing arts. That's fine. You might just do this as a hobby. This doesn't have to be your profession. But all right, anyway, so if you are a math major, it's within the realm of possibility you might be interested in getting a copy of Mathematica because it's only going to be helpful for your future classes. All right, so now this thing, I'll tell you what, I'm going to have to double check this. I'm not positive it turned out right. And I don't want to rush through this. So where do we leave off here? Division. I think that we've gotten a lot done today. I mean, a lot. So I think we can feel free to stop right here. I'll double check this example that I was working on. And next time, we're not done with chapter 3. So let's not do any more problem sets just yet. Why don't we just hold on to that? And next week we'll finish 3 and then we'll start 4 and then we can do some more problem sets. Now, I have to look it up in my schedule, what chapters are intended for the first midterm. I think it might be 1, 2, and 3, but I'd have to investigate that. So if that is the case, at some point we'll start reviewing for the midterm and then I'll send it to you and you'll be able to do it at home like any other take-home test. And I'll give you, at least a week to do it. You'll be able to consult all your notes, the videos, everything. And you can still ask questions. So it won't be that much of an ordeal, I hope. All right. Oh, do you have a question?
Yeah, thank you.
Go ahead.
Where do we take the midterm? Like when it does
At
happen?
home. You just download it and then write it out on paper as if you were sitting in the classroom. And when you're done, either you scan it with one of those cool software packages on Apple, or else you just take pictures of it with your camera and email. Yes,
is
go
it
ahead.
cool if I just use my tablet and pen?
Sure, absolutely. Does that create documents that you can email to me?
Yeah.
It does. Well, then there you go. Perfect. I like that idea.
Thank you. I just want to make sure.
Sure, absolutely. Anyone
And,
else? Oh, go ahead.
how many questions are there going to be on the midterm?
Oh, it won't be, no, it won't be like a massive ordeal. Think about it this way. This class normally meets in person. I always made sure that the in-person test did not take more than 2 hours or so, because, that's a long time. And anything beyond that, you're starting to get worn out and everything. So I always I always try to make sure they took less than 2 hours. So the same thing will hold here. In other words, if you sat down and did it from start to finish, you should be done within 2 hours. How many questions that is, I don't remember, but the time frame which you should be able to do it is roughly 2 hours. But you can take more than that. You can take all the time you want. Like I said, you'll be doing it at home. You'll have access to all your materials, and I usually give it like a week or so to everyone to finish it. So time will not be an issue at all. All right. And the level of the difficulty, it'll be exactly the same. It'll almost be like you're doing the problem sets all over again. Let's put it that way.
Yeah.
It's exactly the same.
One other question. Is like the review that you're giving, is it like, is a midterm similar where like, this is the type of questions you're gonna get on the midterm to the from the review? You know what I mean?
Yes,
Like,
exactly.
gotcha.
Yes. The review is basically like more problem sets all bundled together. It's just that it's covering, 3 or 4 chapters instead of just one. That's really
Gotcha. Well, thank you.
okay. Yeah. So I'm reassuring you all, I hope, that it's not going to be a nightmare. It's just going to be what we're doing here. That's literally all that it is. And so after you've gone through the review for the midterm, you'll have had so much practice that you should have no trouble at all with it. Okay. So anyone else have any questions? So, all right, we'll stop here. I'm sure you're all worn out, and but you had, it's a good kind of worn out, isn't it? It means you've accomplished a lot today. You can feel free to have fun for the rest of the day, I guess, unless you have more classes this afternoon. But even if you do, they won't be as hard as this. So yeah, we're good. So why don't you go home all right, if you're already home, stay at home and have fun today. And we'll just pick it up right here when we left off. There's no more problem sets between now and next week. We'll just carry on from here.
Have a good day, sir.
All right, see you later.
Yeah.
All right, bye. Oh, Fernando, yes.
Hi, sir. I sent you a comment on the chat.
Oh, I didn't see them all. Sorry. What does it say?
No, I just wanted to ask if I could be able to ask you a personal question on one, just you and me, if that's it's not a problem.
All right. Yeah, I think we'll wait till everyone.
Yeah, it's not too long. I just wanted to ask you real quick. It's
All right.
important.
All right. If anyone else in the meantime wants to ask anything. Okay. We have a lot of people in this class who don't want to stop learning math. I'm very impressed by that. Okay. All right. I guess I'm not sure what's going on. I'll just get them. I can send them home. I didn't realize I could do this. I'm not being rude. I don't want to be rude to these people, but okay. I didn't know I could even do this. All right, now there's literally just you and me. Okay, go ahead.
I noticed you're still recording.
Oh, do you want me to stop that? All right. Nope,
yes,
nope.
please.
Now let me. I'll tell you what. I'm going to stop the
Sure.
sharing.
Yeah.
Now, if this cuts us off, though. No. Oh no. Here it is. I have an easier solution. Hold on. What am I thinking? Pause share. There it is. Good point. No, I'm sorry. I'm glad you reminded me. I completely forgot about that. So now, not only is there nobody else in this room, but nothing is being recorded. The recording has stopped.
It said it's still recording though. I don't know why.
Doesn't really say that. Oh my.
Yeah, I
God.
still see the blinking red light.
Oh, I know what it is. The screen sharing is paused. All right, okay, let's see. What other options do I have? All right, well, you know what? Let me,
Would you want me to join you? Would you want me to join like another Zoom call? If that will make it easier.
well, let's find out if it's necessary. See, if I say end the meeting, I'm afraid that we're just gonna get chopped off. So, you know, it might be easier. Why don't you put your email address in the chat room?
Okay.
I'll create a Zoom meeting. That will be, you know, not recorded or anything. Okay. I mean, I think I know what your email address is. It's just your name. First, oh yeah, that's pretty okay. First, last
Yep.
name at
Yep.
purchase. All right. Now I'm going to stop this meeting and it probably will. Okay. So what I'll do is I'll go back into Zoom and create a quick new meeting for both of us. As soon as you
All
get
right.
the invitation to it. All right.
All right. Sounds good.